Okay, so esters. So let's talk about esters. Esters, we have been working with esters as this idea of the carbonyl, oxygen, carbon. Okay, so this is the ester functional group. All right? We left off talking about nomenclature of esters. So if I take an ester and I make a specific ester, that might look like this. Okay, that's a specific ester. I take my blue pen, I cut it in half, right? And the side with the carbonyl is my base. So this side has the carbonyl, this is my O branch. So this has 1, 2, 3, 4, 5, 6, 7. So that's going to be heptanoate. Okay, heptanoate. So this is all named with the word heptanoate. What type of heptanoate? Oh, I have a butyl heptanoate. So it's a butyl heptanoate, right? Good? Now the reason why I go through this exercise of the blue pen, of cutting this thing in half, is because now we're going to see the chemistry of esters, right? The chemistry of carboxylic acids and esters is really the important aspect of them. Nomenclature, physical properties. The physical properties of esters are that they're very sweet, they have a really nice aroma. But the chemistry is really important. And here's what's going to happen. I'm going to see that the ester is broken right where this blue line is, right where I name it. The same line that I used to name it is the line that I used to break it and do its chemistry. Okay? So here's what happens to esters. Esters under hydrolysis conditions acid, water, and heat, they're going to break up. Okay? So notice that the functionality that just happened here. I'm going to take an ester and I'm going to hydrolyze it to a carboxylic acid. And an alcohol. Okay. So that's its chemistry. So I take an ester under hydrolysis conditions. Hydrolysis conditions are acid, water, and heat. I'm going to actually break this molecule right there. Okay? And what actually happens is I'm going to put an OH here and an H here. Okay? So acid hydrolysis of an ester breaks the bond at the same location that we've been using to name the ester. All right? So it puts water across the ester to form an alcohol and a carboxylic acid. Okay? So here's kind of the neat thing. If I can name it, I know my products. If it's butyl heptanoate, it's going to be the products of butyl heptanoate under hydrolysis. Okay, is going to be butanol and heptanoic acid. Does that make sense? So that same blue line that names it is the same blue line that hydrolyzes it. Okay? So you can see that this is going to become the alcohol. So the butyl goes to the butanol. Parent name of the O8 becomes the oic acid. Okay? Good? Your turn. What are the products of the hydrolysis what are the products of the hydrolysis of this this ester? Hydrolyze that. Okay, so if you can name it, you can hydrolyze it. So my blue line goes here. This is going to be 1, 2, 3, 4, 5, 6. So it's going to be hexanoate. 1, 2, 3, 4 is butyl. So the molecule itself is butyl hexanoate, which tells me my products are going to be butanol plus hexanoic acid. Okay, so butanol is going to look like this. That came from basically putting OH across that blue line. All right, that's what that line is doing. So this one is my butanol, this one is my hexanoic acid, so it looks like this. Okay. Okay. So esters hydrolyze to carboxylic acids and alcohols. Okay. So let's make sure we're tracking. Let's do one more. Challenge you a little bit. It's always good to be challenged a little bit. What is the hydrolysis product? Of this. Okay, so blue pen between the carbonyl and the oxygen, that's where it's going to cut. Carbonyl has the benzene ring, so this was benzoic acid, or excuse me, benzoate. What type of benzoate is it? Well, it's 1, 2, 3, 4, 5, 6, so it's hexyl benzoate. Benzoate. Hexyl benzoate, which means my products under hydrolysis are going to be hexanol and benzoic acid. So hexanol looks like this, or actually benzoic acid looks like this. There you go, there's your two products. Look, that's pentanol. Okay. Questions on that? Yeah.
There's another carbon between the benzene and then the one row. Would it be named separately?
Yeah, that would be a little brutal.
Oh.
If I gave you that, it'd be kind of mean. That would be kind of mean. So if you want to know what this would be, this would actually be 2-phenyl ethanoate. So ethyl 2-phenyl ethanoate.
So you're not.
No, I won't do that to you.
Okay.
Because here's your longest chain right here. It's 2, 1, 2. Here's a substituent coming off. That's how you name that. I won't do that to you. Again, it's not a course in nomenclature, but we have ways to do it. It's just not for us. Okay? We're comfortable with the products. Yes?
Does it matter what way you put the products in order?
Nope, not at all. Not at all. You can write those, and you can write them upside down. You can write them, yeah, it doesn't matter at all. Flipped all over the place. Okay? Are we good on that? Okay, so the next thing that we're going to do is we're going to see that carboxylic acids, when they react with alcohols, make esters. Huh, that's kind of interesting. So if I take a carboxylic acid and an alcohol, I make an ester. So carboxylic acid, carboxylic acid plus acid goes to okay. So what happens with these carboxylic acid, so carboxylic acid plus an alcohol over an acid goes to an ester and water. Okay? So carboxylic acids react with alcohols to do a dehydration. This is a hydration. Hydration adds water. Dehydration removes water. So you can see water is right here. So if I remove water, notice I'm making a new bond between the carbonyl and the oxygen. So over here, my new bond is this red bond right here. That is my new bond. Again, remember what a bond is. Bond is the movement of two electrons. That's it. It's nothing mysterious. I'm going to put two electrons, these two electrons here, okay, to make a new bond. So those are right there, okay? So carboxylic acids and alcohols dehydrate to form esters. And again, nomenclature helps us. This here is what? Well, this is butanoic acid. This is propanol, N-propanol. So that's going to go to propyl butanoate. Okay? So that's where the nomenclature actually lines up with the chemistry that I'm learning. It's kind of cool. So if I can name it, I can follow the chemistry. So let's have you practice one. Make sure see one, do one, teach one is working for us. Okay. So what would the reaction? What would the reaction of this alcohol plus this carboxylic acid with acid? Okay. What would the reaction be? What would my product be? Okay, so if you want to do the nomenclature way or the reaction way, what I'm basically going to do per this over here is I'm going to put a bond between this oxygen and that carbonyl. That's my reaction. Okay? So the product from that is going to look like this. If you want to do it the nomenclature route, this is hexanol. This is benzoic acid. This is hexyl benzoate. kind of cool? So the chemistry and the nomenclature help us. We good on that? Okay? Now, that said, when we're actually working with esters, and we're working with carboxylic acids, you might ask yourself the question, aren't these just reversed reactions? And the answer is yeah, they are. Okay? They go back and forth. So here's the thing. If I want to force it one way or the other, if I want to go to the ester, I either have to do one of two things. I have to eliminate, if I want to get Le Chatelier's principle to move equilibrium to the left, I either have to move water, and you can do that. You use what's called a Soxhlet distillation head in your distillation apparatus. You can do that in the lab. The easier way to do it is to increase the concentration of alcohol. So if I increase the concentration of alcohol, I'm driving it that direction. If I increase the concentration of water, I go that direction. Okay, and that's the way we do this. So that's why this reaction here, going that way, has water. It drives the reaction that way. This reaction this way does not have water. Okay, it has quite a bit of alcohol. So if Dr. Nagels actually does this experiment in lab, and I hope he does, it's a fun one, it'll be a ton of alcohol, a little bit of acid, and your carboxylic acid, and you'll make the ester. Okay? So they're reversible reactions. Now, what's interesting about this, if you take a molecule like salicylic acid, so salicylic acid is one of the classic organic molecules that was discovered around the turn of the 20th century. Salicylic acid looks like this. Okay, that's salicylic acid. Salicylic acid is an antipyretic. It reduces fever. It's discovered by Bayer, and the actual one I'm going to show you was discovered by Bayer, was synthesized by Bayer. But what happens with salicylic acid, it's pretty acidic in the stomach. And so people were like, ugh, when I take it, yeah, it's going to reduce fever, but my stomach is on fire. And so the very first attempt at fixing that problem was to react it with sodium hydroxide and to form what you would know as the salt, because we know salts are from acids and bases. And so this was the first attempt to try to get rid of the acidity within the stomach. And it's actually active. It's actually very, very, very good at what it does. The problem is people would not take it. And the reason they wouldn't take it is because it was horribly, horribly sweet. Kind of tastes like artificial sweetener. And today, people like artificial sweeteners. All right? But back in those days, it wasn't acceptable. So what Bayer figured out is, okay, well, I can't get people to take it this way, can't get people to take it this way, so I'm going to go ahead and react it with an anhydride. You don't need to know what an anhydride is, I'm not going to go into that functional group. But actually made this form of salicylic acid Okay, so he put an acetyl group on it. Notice the functional group here. Oh, that's an ester, right? Here is my special bond. Here's the carbonyl, so it's ethanoate. And you can see that this is acetyl salicylic acid. That is today what we take when we take an aspirin. That's Bayer. Okay? And this is the Bayer synthesis. This is the compound. Probably still the #1 compound ever synthesized and consumed by the public, all right? And we're talking this thing's made in like trainload quantities, massive, massive amount of that, all right? Where else do we see the functional group, the ester functional group coming from something like an alcohol or carboxylic acid? Well, here's another place where we see this process, which is, I think, pretty fascinating, because now it's kind of coming full circle from some of the very first things that we talked about on our first day together, our first lecture together. And that is when we draw these structures of these molecules. One of them is, you'll see this one here. Okay, so now you're starting to be able to identify, oh, well, that's a carboxylic acid. I'm good with that. Right, so this is ibuprofen. Okay, and you can see that, oh, okay, well, now I know that's a benzene ring. I know this is a propyl group, a butyl group actually. Methyl coming off, it's chiral, because that's a chiral carbon, carboxylic acid. So now you're starting to see, oh, wow, we've actually come a long ways since day one looking at the periodic table. All right, one of the other ones that you might remember, maybe, probably not, but is this one here. Remember this one? So when you start to now look at these functional groups, anybody remember that one? What was that one? That's morphine. Notice that morphine has 2 alcohols. When I react an alcohol with a carboxylic acid, what functional group do I get? An ester. So if I take morphine, the alcohols of morphine reacting with carboxylic acids of ethanoate, or ethanoic acid, I put 2 esters on here. And I just went from morphine to heroin. Okay? Heroin is the diester form of morphine. And that's one of the most destructive drugs in our society today, even in the Valley. My wife sees lots of heroin positive patients. Yeah. Between meth, heroin, and fentanyl, we've got some problems. So, yeah, it used to be just caffeine and nicotine. Yeah, we got some big.
You know, it's pretty interesting that just a little tweak can go from something that's really, you know, that's good to something that's only destructive.
Isn't that true? Isn't that true? Especially, and heroin used to be accepted. I mean, that was Sherlock Holmes' drug of choice, right?
Yeah.
Can you show again what you or how you modified morphine to come up with the SRX 111?
Oh, that's
the drug that you created.
yeah. We'll get to that. That's SNX 111 is a 21 amino acid peptide. When we get to proteins, I'll explain that. Yeah, so basically, when I was in the industry, we isolated a toxin from a sea snail off the Sea of New Zealand, off the shores of New Zealand, and in that sea snail, we systematically identified all the compounds. This little sea snail is injecting 40 compounds into its fish. We're like, that's kind of weird. So we went through and we isolated them all. Turns out one of them is an N-channel blocker specifically for pain. So this little guy's actually being nice to the fish and anesthetizes it before he eats it. So we took that molecule, synthesized it, upscaled it. Turns out that it's 10,000 times more potent than morphine with no addiction, no side effects. And the FDA fast-tracked this, and we're all millionaires overnight at school. Yeah.
So you're telling me that the drug that they developed from the cones, now venom, you're the one who created it?
It was my research team, yeah. It's like Iconitide, I won the patent, Creole, yeah. Isn't that kind of cool?
That's amazing.
Like, yeah.
I read about all that in.
Oh, did you go?
Yeah, the whole.
Yeah, that was my whole team at Barracks Corporation. We got bought out, when I was there, we got bought out by Elan Pharmaceuticals, which was this giant Irish holding company. So yeah, it's pretty cool. Pretty cool team. Yeah.
So, I feel like some babies can be born addicted to things like heroin and
Yeah, yeah, yeah.
Does that affect them their entire lives? And like, how long term is that?
That's a really tough question, Hannah, because we're now learning this whole process of methylation in the first, especially the first trimester, that the mother, and this isn't like, oh, blame it on your mom type of thing, but what's happening during development of the fetus during those first 3 months, the DNA is actually being tagged to what she's experiencing. So if it's called epigenetics if you want to Google that. It's really fascinating. Epigenetics is the methylation of the DNA while the child is being developed in the womb. And so the predisposition for heroin for that child, if she's doing heroin during that first trimester, yes, that baby has a high probability of having disposition for that. Still doesn't have to be a heroin addict, but the probability, that's why generational curses, it's a biblical thing, right? If your grandfather was an alcoholic, your dad's an alcoholic, your chance of being an alcoholic is actually pretty doggone high. Why? Because again, it's a generational thing. It has to be broken. Okay, so that's a really good question.
I just have to ask, because this is the one part of that I could not find in any of my studies, what actual protein in the cone snail's venom was the one that you could synthesize to make the painkiller from? Because I know most of them are neurotoxins, so lethal that they can kill you in a matter of seconds.
Absolutely.
So what protein did you actually synthesize from that to use as a painkiller?
I'll show you. When we get to proteins, I'll show you. I'll show you because the hardest part is iconotide. Is that it has 6 cysteines. So there's and basically there are 6 squared, or 3 squared is 9. So there's 9 different ways to bring that thing together, and there's only one that is iconotide. So I'm gonna explain all that when we get there. Okay? Yeah, it was cool. It was cool work.
I love
Much. What? Do you like cone cells?
Yeah, because like the way I've always thought of it, most venomous animals, their venom is like, let's just look at elapids, for example. Their venom is hyper concentrated to take on a very specific prey item, and it works very effectively against rodents. Cone snails, it's almost like they went to the venom stores like, ooh, I like this, I like this, I like this, I like this, I like this.
Exactly.
They threw everything in the kitchen sink in there.
It's amazing how much that little guy was injecting. You know, and then it specifically blocked the end type, that bad pain. You don't want to block good pain.
Yeah.
Right? There is good pain. Good pain looks like this. Oh, that's hot. Get your hand off it, right? That's good pain. You don't want to, I have no pain. And there are people that are born without pain receptors. Very rare disease. You have to be really careful because you need good pain. It's a tech. Yeah.
Do you know what kratom is?
I don't. I'm not sure familiar with that. You just something fascinating with it. Okay. I'd like to know. Okay, so esters and carboxylic acids, right? I think it was Christian or it might have been Jack said, isn't it amazing how fast we can go from something good, right, to something destructive? And that's true. But even hydrocodone or oxycontin or oxycodone basically looks like this. This is oxycodone. Okay. So you remove the alkene and you oxidize that, and that's the difference between those. But they're highly addictive drugs, highly. And we'll get into why that is when we start to see the enzyme and the protein structures with what these things fit into. Okay. Now, yes.
So with the esters, you've been attaching all the hydrogens to it, so it's not like alkanes and alkenes where the hydrogen is implied, or you need to write it out.
On the carboxylic acid?
Yeah.
So here the rules, there are some subtle rules that I'm not going to get into with when we imply and when we don't. Technically, you only imply a hydrogen that's on an sp3 carbon that's not chiral. That's kind of the technical, and that's an ish. Not everyone even obeys that. That's why this is a chiral center, so I put the hydrogen on. But I can imply that there's a hydrogen there. All right, there's a hydrogen there. I know that. You don't imply, and if it's a non-carbon, if it's a heteroatom like a nitrogen or oxygen, you have to put the hydrogen on. So we don't typically think of a carboxylic acid as that. Neither do we think of an aldehyde as that, right? Those just look weird. So we don't imply the hydrogen on carboxylic acids or aldehydes. Does that kind of? Okay. What do you want to do? You want to go more esters Do you want to go more acids? Do we want more alcohols? Do we want to go more NSAIDs? Do we want to move on into amines and amides? About 7, or we want to call it. It's Friday, we could call it. You guys want to call it early today? Let's call it early today. We never do that, right? You got your money for it. We'll pick up, so we'll start off with amines and amides on Monday.
I love toxicology. I know that like
Or whatever you're going with. If you're going to the human retreat, you know.
But I definitely.
All right, yeah.
Cool.
And that's fine.
Cool.
Oh, okay, yeah. No, I think I might try to go through myself. Just gas is $5 a gallon, so.
I can try and set it.
Okay, yeah.
Why don't we make sure?
Yeah, maybe,
Yeah, I will. Awesome. Yeah, you bet.
yeah, sorry, I kind of went out of it.
Yeah, I saw you were sick.
Better. I had a really, really bad case of this. So yesterday I compared.
Yeah, it's a stimulant. Yeah, it's got it's going to mimic dopamine.
because after that they started studying a lot of venom. They have a monster that they have upstairs.
Yeah.
They try to do the same thing with this venom.
You just switch a couple things.
That's a different family. That's goes down for vegetable. No, I think it's similar to Adderall. I don't like it. I'll look that up. But let's go. Let's go. Let's go. Wait a
That's what I wanted to do for the longest time.
No, I did not say that. You said you think I'm a druggie and I lost my grab. I'm just sitting over there with it.
No, that's totally cool. That's awesome. That's awesome.
If we want to make drugs, we gotta come.
Right? We can make those.
We will ask.
You did. You did that reaction right there.
Yeah.
Cool.
I was talking to someone like my engineer friends and they had Jerry.
Uh-huh.
And he like would come and he'd be like, yeah, you guys here, like I could easily just, you guys have all this stuff to make that. Well, like in the chemistry lab.
Oh, yeah.
or in there,
Oh, we could make really
like,
good
look at the
meth.
meth lab and we're like, it does, like, just powder.
Yeah, powder and everything.
Yeah.
Did you already ferment it? Sweet. That's
She
awesome.
was like, I mean, technically this is that, but you guys keep drinking.
You can't drink it. That's right. Yes, that's awesome.
All right, well,
Let's go. Have a great weekend.
yeah,
let's
you
go.
too.
Good for you. Chemistry, right? Yeah. Well, it's different chemistry than what you would be in general chemistry, right? Organic is just its own beast because you're working with carbon. That's what the chemistry does. So it's kind of fun though, right?
No, yeah, it was cool. I was kind of sort of drawing from chemistry and taking it just like whatever like a normal person would understand.
Yeah. Well, I love, and that's why I love it so much. I love teaching it. I love, it's so relevant to like culture and society,
Yeah.
health, and there's so many areas that, just 4 molecules up there. Well, 3 molecules up there that will change the world.
Mhm.
And then when we get on Monday, we're gonna talk about actual penicillin, the whole cylinder.
Yeah,
Why is that? That's probably the miracle, like I said, of all time.
Yeah.
So,
Let's go. Yeah.
let's go. So Cooper, are you gonna hook up with your mom now?
Yes.
Okay, so you're good to go?
I am good to go.
All right, my